Hi friends, I myself, Dr. Adarsh Mangal, working as Assistant Professor, Department of Mathematics, Engineering College Ajmer. Today I will deliver a lecture on method of separation of variables for second order linear partial differential equation with the solutions of one-dimensional heat equation, one-dimensional wave equation and two-dimensional Laplace equation. Firstly, what is the method of separation of variables for second order linear partial differential equation? Now let us suppose the standard form of second order linear partial differential equation is RR plus SS plus TT plus PP plus QQ plus ZZ equal to Fxy, where R, S, T, P, Q, Z and F are functions of x and y only, can be solved by the method of separation of variables. Now let us suppose that Z is a function of capital X and capital Y, where capital X and Y are the functions of small x and small y only. Then equation 1 takes the form 1 by capital X f dx is equal to 1 upon y g d dash capital Y, where fd and gd dash are quadratic functions in D, where D is del by del x and d dash is del by del y respectively. And now the equation is separable in the variables x and y. Equation 3 can be reduced to two second order ordinary differential equation, and it is observed that the left hand side and right hand side of 3 are functions of x and y respectively. X and y are independent variables, so that the two sides of 3 will be equal only when each is a constant. Say 1 upon x f dx is equal to 1 upon y gd dash y is equal to k constant. So that we can have fd is equal to kx, fdx is equal to kx, gd dash y is equal to ky. Equation 4 can now be solved by the method of ordinary differential equations, linear differential equations with constant coefficients. The general solutions of 4 will depend on the choice of k, either positive or negative. Now we move forward to find the solution of one-dimensional heat diffusion equation. One-dimensional heat equation is, this is standard form, k del 2u upon del x square is del u by del t, equation 1. Here u is the dependent variable which depends upon x and t, two independent variables, so that we assume the solution of 1 be of the form uxt is capital X depending upon small x and capital T depending upon small t. We then find, on substituting in 1 after differentiating partially with respect to u, after differentiating partially u with respect to small x and small t, we have x double dash upon x and t double dash upon kt, where the dashes denotes derivatives with respect to the relevant variable. The left hand side of equation 3 is a function of x and right hand side is the function of t. X and t both are independent variables, therefore 3 can hold good. 3 means equation 3 can hold good if each side is equal to a constant, say mu. So that here x double dash minus mu x is 0, t dash minus mu kt is 0. Three cases arises according as mu is 0, positive or negative. Let mu is 0, then solution is x double dash is 0, so that x is a1x plus a2. T dash is 0, so that t is equal to some constant a3. Let mu be positive, say lambda square, then x double dash minus lambda square x is equal to 0 and t dash minus lambda square kt is equal to 0. On solving these differential equations with constant coefficients, we have x is b1 e power lambda x plus b2 e power minus lambda x and t is equal to b3 e power lambda square kt. Case third, when mu is negative, say minus lambda square, then we have x double dash plus lambda square x is equal to 0 and t dash is equal to minus lambda square kt. On solving these linear differential equations of second order, we have x is c1 cos lambda x plus c2 sin lambda x and t is equal to c3 e power minus lambda square kt. Thus the three possible solutions are equation 9, 10 and 11 respectively when k is 0, k is lambda square and k is minus lambda square. Now we have to choose that solution which is consistent with the physical nature of the problem, since we are dealing with the problem of heat conduction. So the temperature must decrease with the increase of time. Accordingly, the solution given by 11 is the only suitable solution. Now we move forward to find the solution of one-dimensional wave equation. A standard equation is del 2u upon del x square is equal to 1 upon c square del 2u upon del t square. Here written one-dimensional heat equation by mistake. It is one-dimensional wave equation. Now, solution of 1 be of the form uxt is capital X depending upon small x, capital T depending upon small t. We then find, after differentiating partially u with respect to capital X and capital T, we have c square x double dash t is x t double dash, where the dashes denotes derivatives with respect to the relevant variable. The left hand side of 3 is a function of x and right hand side of 3 is a function of t, and x and t both are independent variables. Therefore, equation 3 can hold good if each side is equal to some constant, say mu. So that we have x double dash minus mu x is 0, t double dash minus c square mu t is 0. Now, also three cases arise as the previous one-dimensional heat equation. Let mu is equal to 0, so that we have x double dash 0, x is equal to a1x plus a2. T double dash is 0, t is equal to a3 plus a4t. Case second, mu is positive, say lambda square, then x double dash minus lambda square x, t double dash minus c square lambda square t equal to 0. Solving these differential equations of constant coefficients, we have x is equal to b1 e power lambda x, b2 e power minus lambda x, and t is equal to b3 e power c lambda t and b4 e power minus c lambda t. Now case third arises when mu is negative, then say mu is minus lambda square, then x double dash plus lambda square x is 0, t double dash plus c square lambda square t equal to 0. Solving these differential equations of second order, we have x is equal to c1 cos lambda x plus c2 sin lambda x, and t is equal to c3 cos lambda ct plus c4 sin lambda ct. Now the possible various solutions are equation 9, 10 and 11, whereas k equal to 0, k is equal to lambda square and k is equal to minus lambda square respectively. Now we move forward to find the solution of two-dimensional Laplace equation. Two-dimensional Laplace equation is del 2u upon del x square plus del 2u upon del y square equal to 0. It is a standard Laplace equation in two dimensions. Equation 1, where u is the dependent variable, x and y are the independent variables. So, solution of equation 1b of the form uxy is capital X depending upon small x, capital Y depending upon small y. After differentiating partially u with respect to x and y, we have x double dash y plus y double dash x equal to 0, where the dashes denotes derivatives with respect to relevant variables. The left hand side of equation 3 is a function of x alone and right hand side is the function of y alone. X and y both are independent variables, therefore 3 can hold good if each side is equal to a constant, say mu. Therefore, x double dash minus mu x is 0, y double dash plus mu y equal to 0. Now, three cases arise. First case, let mu is equal to 0. Then x double dash equal to 0 means x is equal to a1x plus a2. Y double dash equal to 0 means y is equal to a3 plus a4y. Second case, when mu is positive, then let us suppose mu is equal to lambda square. Then x double dash minus lambda square x is equal to 0 and y double dash plus lambda square y equal to 0. Solving these differential equations of constant coefficients, we have x is equal to b1 e power lambda x, b2 e power minus lambda x, and t is equal to b3 cos lambda y plus b4 sin lambda y. Now the last one, mu be negative, say minus lambda square, then x double dash plus lambda square x is equal to 0, y double dash minus lambda square y equal to 0. Solving these, we have x is equal to c1 cos lambda x plus c2 sin lambda x, and t is equal to c3 e power lambda y plus c4 e power minus lambda y. Thus the various possible solutions are equation 9, 10 and 11 as k equal to 0, plus lambda square and minus lambda square respectively. Thanks for being with me. Please like and subscribe my YouTube channel Aadharshila for the videos of mathematical interest.